Hello, in this video I'd like to talk about ranked tree automata. So far I've just been talking about binary tree automata, but if you look into the literature on tree automata, they're likely to be talking about ranked tree automata, because one of the big applications of tree automata is in terms of analyzing parse trees. A parse tree represents an expression, and this can be a mathematical expression or a piece of code or an expression in a natural language like English. And it represents it in such a way that sub-expressions correspond to subtrees. So for instance, if we wanted to represent the expression the square root of b squared minus 4ac, we could represent it as follows. The leaves of our tree are going to be the indecomposable sub-expressions, so our variables and our constants. And then we're going to merge these together when we apply operations between them. For instance, when we take b to the power of 2, we're combining these two subtrees via a node representing exponentiation. The 4a and c are combined by multiplication. And then we combine these two sub-expressions via subtraction. And finally, we apply the square root operator to this entire expression. And so this tree here represents this expression here, and it does so in a way that every sub-expression, every sub-portion of this formula that makes sense as a component of the whole formula, it corresponds to some subtree of this tree here. So for instance, b squared minus 4 does not represent a subcomponent of this expression here, and it doesn't correspond to a subtree here, but 4ac does correspond to a sub-expression, and so it does correspond to a subtree here. Now notice that we have some nodes that have only one child. I guess you can do that with binary tree automata, although there's not really a sense in which this child node is a left child or a right child. But the big thing that we can't do with binary tree automata is we can't have nodes that have more than 2 children, and that happens a lot with parse trees. And the neat thing is that parse trees don't just apply to mathematical formulas. Again, we can use them to represent code, and we can also use them to represent sentences of natural language. Suppose we have a sentence like, I gave the cat a pat on the head. The convention is to draw this as a tree where each word is a leaf of the tree. And then in a unary node above that, we label each leaf with what sort of word it is. Words like the and are determiners. On is a preposition. And just like we did with the math formulas, we want to merge these nodes together when they form sub-expressions of the entire sentence. So for instance, the cat, a pat, and the head are all phrases that represent nouns, which we represent as NP for noun phrase. And then we understand a preposition followed by a noun phrase to represent a prepositional phrase. I'm going to say that this prepositional phrase here modifies this noun phrase here. I guess you could also say that it modifies the verb, but I think it makes more sense to say that it modifies the noun phrase. And the test for this is to look at the corresponding sub-expression and ask yourself, is this a sub-expression of the original sentence? Is a pat on the head a sub-expression of the entire sentence? Is this kind of a coherent part? And I feel like, yeah. And so together, this whole sub-expression is a noun phrase. And then we have a verb that, in this case, takes 2 objects, the thing being given and the thing being given to. And so this whole thing here, verb, noun phrase, and noun phrase, is a verb phrase. This noun by itself is a noun phrase by itself. And I'm really only doing this so that we just need one rule, which is that a noun phrase followed by a verb phrase is a sentence, as opposed to having to say also that a noun followed by a verb phrase is a sentence. It's very common to look at these sorts of parse trees in computational linguistics, and they're a really powerful tool for describing a lot of grammatical constructs, at the very least in English. It's certainly not a perfect model, and it's not clear how much it represents how people actually think about language, but it is very powerful, particularly if you're trying to have a computer understand language. And just like our math parse trees, these sorts of parse trees also sometimes require nodes to have more than 2 children. And so if we want to analyze these things via automata, we're going to need automata that can handle trees that have nodes that have more than 2 children. One way of doing this is by looking at our parse tree as a ranked tree, a tree whose nodes are labeled by elements of a ranked alphabet. So a ranked alphabet simply assigns to each character in our finite alphabet a rank, an arity. And when we label trees from our ranked alphabet, any node that we label with a particular character C must have the arity of C children. So for instance, in order to be able to view this parse tree as a ranked tree, it needs to be the case that each of these symbols has an arity associated to it. Our leaves, which have no children, have to be assigned arity 0. Our square root function, because it has 1 child, has to have arity 1. Our exponential function, because it has 2 children, has to have arity 2. And here's where things get a little bit weird. This particular multiplication, it has to have a fixed arity to it. So actually we want this to be like a, I don't know, we need to somehow indicate that this is multiplication, specifically multiplying 3 things together. If we want to have parse trees that offer multiplying 2 things together or multiplying 4 things together or whatever, we're going to need separate characters for each of those numbers of children, because each of those different characters is going to have a different arity to them, a different number of children that it's allowed. So ranked trees don't quite correspond to the way that we think about parse trees, and we're going to need some more advanced tools in order to be able to analyze trees where a node with a particular character has an arbitrary number of children. It turns out things are much easier if you can put this restriction on the number of children of any one particular node. And actually this gives you, because there's only a finite number of characters in the alphabet, it gives you a global upper bound for the number of children of any node on your tree. And that's really nice when it comes to defining automata. Once we have a notion of ranked alphabet and ranked tree, we can define a deterministic ranked tree automaton. We can specify a deterministic ranked tree automaton by first specifying a ranked alphabet and a finite set of states, and then for each character in the alphabet we're going to have some sort of transition function. If a node is labeled with the character C, it has to have arity of C children. Each one of those is going to get a state assigned to it as we kind of work our way up from the bottom of the tree. And this function here tells us, given all of those states, what state we should assign to the node labeled C. And then we have a set F of final or except states, and when we work our way all the way up to the root and work out what state to assign it, if we assign it a state in the except states, then we say that we accept the whole labeled tree, and if not, we say we reject the whole labeled tree. I want to draw your attention to an important subtlety here, which is that this structure here can be specified by a finite specification, right? We only need some sort of finite data structure in order to describe, in order to store these things. And that's because there's only finitely many functions that take in the arity of C inputs from Q, a finite set, and output some element of that finite set. But importantly, if we didn't restrict the nodes labeled C to have exactly some fixed number of children, then we'd have to specify a transition function for every number of possible children. A transition function if we don't have any children, a transition function if we had exactly one child, a transition function if we had exactly two children, and so on and so forth. That would require an infinite specification. And that's not really something that I'm interested in. Remember that my interest in automaton is because they correspond to formulas in various logics. And if our automata took an infinite amount of data to specify, then the formulas would also require an infinite amount of data to specify. We'd have an infinite formula, and that's usually not something, well, I guess there are logics that do that, but they're not the ones that I'm studying. So the fact that we're restricted to ranked trees is a really important subtlety, and again, I'll talk about what happens if we want to deal with unranked trees in a future video. Let's do an example. We can parse a Boolean logic expression involving true, false, not, and or, and we'll get a parse tree. And suppose that I want an automaton that looks at that parse tree and tells me if it represents a true formula or a false formula. We have something like true and not false. If we parse this, we get a parse tree that looks like this. In order to specify this automaton, we're going to need to specify a ranked alphabet of symbols that go at nodes in the tree. True and false don't have any children. We always expect to see them at leaves, and so they're going to be rank 0 characters. Negation is going to be a rank 1 character. We expect it to have exactly one child, a node corresponding to the subexpression that gets negated. And or are going to label nodes that have 2 children, so they're going to be characters of rank 2. In order to evaluate our formula, we literally just need to evaluate it, keeping track as we work our way up the tree, as we work our way from the inside of the formula out, of whether or not we have a true subexpression. And so our set of states is just going to be, we need one state for if our current expression is true. I'll use 1, and one state for if our current expression is false, and I'll use 0. Then we need to specify transition functions for each character. For true and false, they're going to be functions that take in 0 inputs and output an element of Q. These are just constants. I guess if you really wanted to, you could write this as delta t of nothing is equal to 1. And delta f, again, we're going to want to specify a constant. If we're looking at this sub-expression here, it evaluates to false, and we're using 0 to represent false, so it's going to be the constant 0. Our negation symbol has rank 1. We expect it to have one child. And we're going to specify a transition function for it that takes in one element of Q and outputs one element of Q. In particular, if the child of our node corresponds to a false statement, then our node is going to correspond to a true statement. And if the child of our node corresponds to a true statement, then the negation is going to correspond to a false statement. For and or, these are characters of rank 2. Nodes labeled with them have 2 children, and so we need to specify a transition function for them that takes in two elements of Q, two states, the states of the two children in order, and outputs a state for that particular node. And it's exactly what you think it should be. For instance, the transition function for AND of 0 and 1, if the sub-expressions of an AND are false and true, then the whole expression is going to be false. But for an OR, if the sub-expressions are false and true, then the OR of those sub-expressions is going to be true. And our set of except states, we want it to be the case that when we get to the root node, we're looking at a true statement. We have a node that we've assigned the state 1 to. So again, note that if you fill in this bit here, we only need a finite amount of data in order to specify this automaton. And again, that's super important. Let's apply this automaton to this particular parse tree here. We start at the leaves, so we assign delta t to this node here. We assign delta f to this node here. Now that we've worked out the states for all of the children of this node, we can specify the state of this node. It's just going to be, we take the state of the child and we plug it into the transition function corresponding to that particular character. And so that tells us that because the child node is labeled 0, we label this with a state 1. And so our not false represents a true sub-expression of the whole expression. And finally, to work out the state to associate to this node, we plug into delta and 1, 1, which I haven't written out here, but that's just going to be 1. And so we assign the state 1 to the root node, and that's an accept state, and so we accept this parse tree here. And so hopefully you can see that this automaton here accepts parse trees of any true Boolean formula involving these symbols, and rejects we're going to associate a 0 to the root node if we have a parse tree corresponding to a false expression. We can make our automata non-deterministic by turning our transition functions into transition relations. One way to think of this is that our transition function outputs a set of possible states that we could assign to a particular node, given the states assigned to its children, or we can view this as a relation that tells us when a set of states assigned to the children of a node labeled C and a state that we assign to a node labeled C is a valid configuration that can show up somewhere in the run of our non-deterministic automaton. And there's really not a fundamental difference between ranked tree automata and binary tree automata. All of the nice theorems that we had have versions for ranked tree automata. The regular ranked tree languages are closed under complementation, union, and intersection. We have a version of the Myhill-Nerode theorem, we have a version of regular expression, and we can still make sense of leaf-to-root and root-to-leaf ranked tree automata, and they're equivalent in the non-deterministic case and equivalent to deterministic. When I specified deterministic ranked tree automata, they were going from the leaves to the root. But we can also make sense of a deterministic ranked tree automaton that goes from the root to the leaves. It's just not equivalent to any of the other possible automata that we could specify. And so I'm not really interested in studying them. But I have a preference for binary tree automata because their correspondence with a logic is much neater. It's much more direct to correspond binary tree automata and weak S2S, as we saw. As far as I'm aware, there's no monadic second-order logic that corresponds directly to ranked tree automata, but we could, for instance, develop a theory of ranked tree automata and then use that to correspond to weak S2S via some sort of tricky encoding where we're mostly looking at binary trees anyway. Let me actually show you, because this is kind of interesting, how we can translate back and forth between ranked tree automata and binary tree automata. For instance, if we were trying to approach weak S2S via ranked tree automata. Let's say that we have some character C in a ranked alphabet that has arity 4. Then I'm going to want to translate it into actually 3 different characters, C1, C2, and C3, when we construct a corresponding binary tree automaton. And the way this is going to work is that suppose that we have some node labeled C in our ranked tree that has 4 children. And those children might also have children of their own. Then we're going to translate this configuration into, in particular, everywhere we see the node C in our ranked tree, we're going to replace it by a chain of 3 nodes in our binary tree, C1, C2, and C3. And then we're going to take the child nodes and just hang them off in order like this. Now what we need to do is we need to somehow take our understanding of the transition function for our character C, right? This function is going to take in 4 states and output a state to assign to this node here. And we want to somehow come up with transition functions for our characters C1, C2, and C3 in such a way that when we assign the corresponding states to these nodes here, we wind up associating the state that we associate to this node here to this node here. Let's be concrete about this. Let's say we assign states Q1 through Q4 to these nodes here. And again, we need to pick the transition functions for C1, C2, and C3 in such a way that we assign the same state to this node and this node. Now, there are many ways of doing this, but one way to do this is to simply have C3 pass on all of the information that it gets onto C2. So the state that we're going to assign to this node is actually going to be a pair of states of this automaton. It's going to just be the pair 3, 4. And then this node is also going to pass on information. It's going to take in this information that it gets, the state assigned to this node, Q2, and the information it gets from this node, the state, the pair, Q3, Q4, and it's actually also going to pass on the information. And the state we're going to assign to this node is actually the triple Q2, Q3, Q4. And then finally, C1, the transition function for that character, is going to take in Q1 and all of this information here, the states of the child nodes, and work out the state of this node. And it's just going to do that using the same transition function that C had initially. So we have a binary tree automaton whose states are tuples of states of our ranked tree automaton. But luckily, the size of those tuples is bounded. Remember that because it's a finite alphabet, there's a universal upper bound on the rank of any character in this alphabet. And so there's going to be a universal upper bound on the length of the tuples that need to be passed in doing this construction. And so the set of states in the binary tree automaton that we're constructing is actually just going to be finite tuples of states from this automaton up to length, the maximum rank of characters in this alphabet. So we don't have to worry about accidentally introducing infinitely many states. Notice again that we're making heavy use of the fact that every character in this ranked alphabet has a fixed rank. If we had to work with characters of arbitrary rank, characters that could have an arbitrary number of children, then the length of these tuples of states that we would pass upwards in this sort of construction would be unbounded. And so the number of states of this binary tree automaton that we were constructing would also be unbounded. It wouldn't be a finite tree automaton. But anyway, if you take every character in our ranked alphabet that I guess doesn't already have rank 2 and do this sort of translation, then you can translate any ranked tree automaton into a corresponding binary tree automaton that accepts the corresponding binary trees if and only if the original automaton accepted the original ranked tree. And so modulo some sort of encoding, ranked tree automata and binary tree automata aren't really different from each other. I guess if I want to make that claim, I also need to show that we can take any binary tree automaton and translate it into a corresponding ranked tree automaton. And that might seem completely obvious, but there's a bit of a subtlety, so let me show you the construction just so that I can explain what that subtlety is. So the thing that binary trees have, and thus binary tree automata have to deal with, that ranked trees don't have, and so ranked tree automata don't have to deal with, is the fact that there's a distinction between a left child and a right child, and also that characters do not determine the arity of their nodes. And there's various ways of handling that. We could have an A with a left child character, and an A with 2 children character, and an A with no children character, and an A with a right child character. But actually there's a really nice clean way of doing this. And that's to take all of the characters of our original alphabet and assign them rank 2, and then add a new character, bottom, that we assign rank 0 to. And then we can translate our binary tree into a ranked tree over this ranked alphabet. And that's to just copy our tree over and then add in a bunch of nodes wherever there's a missing child and assign those nodes the character bottom. And so now we have a valid ranked tree over this ranked alphabet. We add in a new state to assign to all of the bottom nodes. And then we just define the transition function for each of these characters exactly as you would expect. If a node sees one of the states coming out of a bottom node, then they know that in the original binary tree automaton there wasn't a child to that side, and so they just do whatever this node would do if it doesn't have a left child. So now we can see that up to some sort of really simple encoding, ranked tree automata and binary tree automata essentially are the same. And so if we had any questions about ranked tree automata, we could just take the corresponding question for binary tree automata and translate it through the appropriate encodings and get an answer for ranked tree automata. So they're really not fundamentally different, it's the same thing being presented in a different way. The last thing I'd like to talk about in this video is a really nice, purely abstract characterization of the ranked tree automata. And this goes back to, if we think about ordinary deterministic word automata, we can think of each character as corresponding to some sort of function on the states, and then a word corresponds to some sort of composition of those functions. And then we want to apply that composition to the start state and ask whether the result is an accept state. Well, exactly the same sort of thing happens in the ranked tree case. It's just that now, instead of talking about unary functions, we're talking about some sort of finite collection of functions that can have arbitrary arity that acts on the finite set of states and their compositions. If we have some sort of arbitrary ranked tree automaton and want to figure out what it does when fed in a particular tree, we can imagine that tree as being the parse tree of a particular expression. In particular, it's going to be B of C of B of A and A. And then if we identify each character with its corresponding transition function, or in the case of characters of rank 0, the corresponding constant, and we evaluate this expression, delta A is 1, delta B of 1 is 0, delta C of 0, 1 is 0, and delta B of 0 is 0. We wind up getting the state that winds up getting associated to the root node, and actually along the way of that calculation we get all of the states for the other nodes as well, and then we just check to see if that's an accept state or not. Just like how every word automaton can be viewed in terms of unary composition, every ranked tree automaton can be viewed in terms of a multi-array composition, in particular multi-array composition of the transition functions. So even though they don't correspond directly to some sort of nice monadic second-order logic, there is something really nice about ranked tree automata. So thanks for watching. Please let me know if you have any questions or comments, and be kind to each other.